Okay, so in this video, we are going to look at developing the ideal gas law. So we've talked about a couple of different laws so far, but we've talked about Avogadro's law, which said that V was proportional to N when we kept temperature and pressure constant. We also created the combined gas law, where we said that volume is proportional to temperature in Kelvin over pressure. So now what we're going to do is bring them all together. And now we're going to say that V is proportional to NT over P. So similar to what we did the last time, we want to convert the proportionality to an equation. We're going to use a proportionality constant. Last time we used K. In this case, we use R. Okay, R is the universal gas constant. Okay, and that's going to be the number that we use. So this number is given to you. And it is that R, switch over to typing, so it's a nice clean number, is equal to 8.314 kilopascals liters. Apparently my dog just figured out how to open the screen door by smashing her face into it, per mole Kelvin. Okay, so kilopascal liters per mole Kelvin, although normally I write it as per Kelvin mole, so I'm going to change that so that it looks the same and it isn't different every single time you look at it, okay? So anytime you want to use R, you are going to plug this number in. Basically, the purpose of it is kind of a massive unit converter, right? Look at how many units it has in it. It has kilopascals, liters, it has kelvins, and it has moles. So we're going to be able to use that to cancel a bunch of stuff out. If you think back to when we did gas stoich in the stoich unit, remember we sometimes use this 8.314 kilopascal liter per Kelvin mole. So we do have an equation that uses it, which is PV equals nRT, which is just this equation rearranged. But if you also remember how we did it in the gas stoich, we also could often solve it through unit analysis. So this is definitely a type of question where if you want to use unit analysis, you can. If you want to use the equation, you also can definitely do that. But for those of you that sometimes struggle with rearranging equations but are pretty good at unit analysis, I'd probably suggest that you're better off to just use unit analysis, because then it places everything where you want it to be. If you're using the equation, then again, just make sure you are including your units and make sure that you are canceling your units out to make sure that you've actually solved for what you want. So P is pressure. It has to be in kilopascals. It has to be in kilopascals because that's the unit we have in R. V is volume. It has to be in liters, and that's because in R it's in terms of liters. Okay, N is moles. Obviously moles is moles, which makes sense because we'd be able to cancel out the moles here. R is this number, and T has to be in Kelvin so that we can cancel out here. So the units that you use when you're using PV equals nRT or the ideal gas law have to match up with the units that are in R. Otherwise, you can't actually cancel things out. So this would be a situation where if pressure was given to you in any unit except for kilopascals, you're going to have to convert it, right? You would have to go back to all those different things that we told you were equal to each other, right? So 760 mmHg is equal to 101.325 kilopascals, which is equal to 1 atmosphere, right? So we would have to create a converting factor to do that, to then be able to solve within this equation. So R is a constant. Normally if we were in class, I'd spend some time talking about how we develop R. We also normally do a lab where we kind of experimentally try to figure out what R is. And usually we get something pretty close to what this number is. Obviously, it's not a perfect match because we have errors associated with experiments that we do. But yeah, generally questions aren't really going to ask you to solve for R. They're going to usually ask you to solve for either P, V, or N, or T. So other types of questions you will sometimes get are going to be density questions, okay? Two ways you can approach a density question. Easiest way tends to be unit analysis. Think about the units you want. Everything lines up nicely. The other way you can do it is using the equation and rearranging stuff. I'm going to show you how to do it through unit analysis because really that's the most important skill we want you learning out of Chem 20, getting ready for Chem 30. Okay, so we want to find the density of helium gas at STP. So really, if you look at this question, you might originally think, wait a second, this hasn't actually given me anything. But it has. It's given me STP, right? Standard temperature and pressure. Okay, so at STP, we know that pressure, where's this writing over there? That's not where I want to write. Oh, geez, hold on. Okay, we know that pressure is equal to 101.325 kilopascal. And we know that temperature is equal to 0 degrees Celsius, which is 273.15 Kelvin, right? We always want Kelvin. Only other thing we really know for helium is the molar mass of helium, right? We know it's 4 grams per mole. Okay, and I'm using this because I need to get grams and I need to get liters, and this is going to give me the grams. The other thing that I have is R, right? We always have the ability to use R, and we're going to have to use R because right now we don't have anything with liters in it. So it's 8.314 kilopascals, liters per Kelvin mole. My font went back to red. Hold on. Okay, so I said I was going to show you how to do this one through unit analysis. So if we are solving for density, the symbol for density is going to be a capital D. Okay, the question shows you up here that you are looking to get grams per liter. So I'm going to choose to start with the grams. I know it has to go on top. I look here, it's already on top. So I'm going to go 4 grams per mole. And it really just wants to go back to red all the time. I may just give up and switch to red partway through, we'll see. Okay, so now I have the grams part. I need to get rid of the moles part. So this doesn't have moles, this doesn't have moles. I've already used this, this has moles. So I'm going to use this to cancel out the moles. Right now though, I need it to go up on top, so I'm going to have to flip this over. Okay, so we are going to flip it. We are also just going to change to red because I give up on changing the color. So we're going to have Kelvin mole, right, and we have to put that on the top so that the moles will cancel, and that's going to go over 8.314 kilopascals liters. Okay, so with that, I can get rid of moles. Okay, I need to get rid of kelvins because I'm just looking for grams per liter, so I have to times by 1 over Kelvin. So we're going to go 1 over that 273.15 Kelvin. So now we have the Kelvin in there, which we can then cancel out. Okay, then we need to get rid of kilopascals. It's currently on the bottom, so I need that to go on the top. So we are going to times by 101.325 kilopascals, and that's just going to go over 1. Then I can get rid of the kilopascals. Let's have a look at our units. Here's grams and here's over liters. So we have solved for what we were looking for. So let's see, we're going to do 4 divided by 8.314 divided by 273.15 times 101.325. And we get 0.178 grams per liter as our answer. Okay, so yeah, we definitely sometimes will ask you to calculate density. It's grams per liter. I'm pretty sure if you look in your red data booklet, you will see a couple of pages in, there's a little table that kind of shows you different units and what the symbol for them are, and I'm fairly sure density is on there. Okay. Okay, so next thing to look at is Dalton's Law of partial pressure. So we talk about Dalton's Law mainly because of how we generally collect gases, okay? So what we find is one of the properties we've talked about before, which is that gases are completely miscible. So they are going to mix. So what that means is it doesn't matter if I have a sample that's pure gas or a sample that's a mixture of gases. If they are at the same temperature and pressure, they are going to have the exact same molar volume, okay? So what we find is that when we mix gases, the total pressure is equal to the sum of the partial pressure of all the gases that are there, okay? So Dalton's law of partial pressures says in a mixture of gases that do not chemically react, the total pressure is the sum of the partial pressures of each individual gas. So what that basically means is that the total pressure is equal to the partial pressure of gas 1 plus the partial pressure of gas 2, right? And if we had more than that, we would just keep adding them all together. Sorry, I'm having issues typing. Plus, new, plus, there we go. I'll just put dot, 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 right? So however many gases I have in there, the total pressure is equal to the sum of each one of those, okay? Apparently I copy pasted that in twice, but that is your Dalton's law. So why that matters is how we collect gases. Okay, so when we are collecting a gas, you are generally going to find that you have a mixture of gases, right? Usually when we talk about collecting a gas, you guys are like, oh, that's really easy. I just put it in a container. The problem, though, is that that container is already full of gas, right? If I take like a cup, let's say, it's already full of gas, right? It's full of air, which is a gas. So for me to collect a new gas in it, I have to get rid of all the gas that's inside of it, right? So how we do that is what we call the downward displacement of water, okay? I wasn't sure if I have a slide on that, I don't. So what happens in the downward displacement of water is we are basically going to fill the container we want to collect the gas in entirely with water. That's going to ensure that we've removed all of the other gases that are there, okay? Then we're going to do why we call it the downward displacement, okay, is generally we are going to have our container. It's considered a bucket, and we are going to fill it up with water. Okay, then we take a eudiometer, which is basically a long, skinny tube that has, doesn't look like a tube right now. I'm going to turn it into a tube. This lovely rounded edge here, okay? Pretend that that's just like a nice tube, okay? So it's going to have marks on it, similar to a burette, although of course you didn't actually use a burette either. But what we're going to do is we are going to start with that tube, and we are going to fill it all the way to the top with water. Then we're going to put our hand on top to cap it and seal the water. We're going to flip it upside down. We're going to stick it into our big water bucket. We're going to take our hand away. And so what you'll find is as long as you filled the tube initially all the way to the top with water, once you flip it over, it should stay filled with water. Then what we do, because it's a very narrow opening at the bottom, is we usually use a funnel, because a funnel is going to stick into there and then it's going to open like this, right? So let's pretend that's our funnel. And then what we do is we take our gas sample and we put it down here. Usually when we do this lab, we use butane. So we use like little lighters. Obviously you're not trying to light them, you're just trying to release the gas. And then you put that little lighter down here underneath your little funnel. And then what you find is that you are going to start to release bubbles. You're going to push the button down and then you're going to see all these little bubbles start to form. And those bubbles are going to travel up the cylinder. Okay, and as they travel up the tube, the water is going to go down. Okay, and that's because we're going to see that the gas is going to start to occupy this space. And the more we continue to bubble the gas, the more the gas is going to occupy and the more it's going to push the water down. And so because there's all little marks for volume on the side of here, eventually we reach a point where we're going to be like, okay, let's just pretend that that's where our gas was bubbled up to. We can figure out what volume that occupies, okay? What we need to do though, before we record what that volume is we need to figure out what the pressure is. I can't actually measure the pressure inside of here, But what I can measure is the total pressure outside. So there's a couple of things we need to do first before we can do that, though. So the first thing I need to do is actually to make it so that the volume of the gas lines up with the water line in here, okay? And I need to do that so that the pressure inside of this tube is equal to the pressure outside. Because I can figure out what the pressure is outside just by using a barometer, but I can't figure out what the pressure is inside. So if this was actually where my volume was, I would obviously be taking the lighter away, I'd be taking the funnel away, and then what I would be doing is I would be pushing that tube down into the bucket. And I would push it down until what happened is that this line lined up with the water in the bucket, right? So what I would basically want to see when I look at it is if this is the water line inside of the container, I would want that to line up with the water line inside of my tube. So when all of this lines up, then that allows for us to say that the internal pressure is equal to the external pressure. Okay, then I can go figure out the external pressure by just going to my barometer and seeing, oh, what's the pressure today inside of this room? And let's say it was 89.9 kilopascals, okay? That would represent the total pressure. So that would be equal to the partial pressure of the butane, which is the gas that I was bubbling up into it. But then the other thing that would be there as well, because I'm collecting this over water, right? Think about what happens if you leave a water glass next to your bedside table. You go back 3 days later, and even though you didn't drink it, it's all gone, right? Even though it's not 100 degrees and you're not boiling the water, it does eventually all evaporate. So what we find is that anytime we collect a gas over water, we're going to collect our gas, but then we're also going to collect water, okay? But the nice thing is I can figure this total pressure out by getting the pressure of the room. I can figure out the partial pressure of water, so I can get this just by knowing what the temperature of my water is. There's all kinds of data tables that you can look at, and they will tell you what the partial pressure of water is at a particular temperature, okay? So you can see here's a table that basically shows you what temperature the water is at and what that partial pressure is. So anytime we would ask you a question like this, we would always give you a data table so that you knew what the partial pressure of water is, right? And as you can see, the hotter it gets, the higher that partial pressure is going to become. So what I would do if I was actually doing this experiment is I would figure out the room pressure to know the total pressure. I would then take my thermometer, stick it inside of the water so that I could determine what the temperature of the water is. Then I'd go look at that data table I just showed you so that I could figure out what the partial pressure of water is. And then to get the partial pressure of butane, I would just do the total minus the partial pressure of the water, okay? So that's how Dalton's Law works, and that's why we care about it, is because we're almost always going to have to account for that water, but we have data tables to let us do that pretty quickly. So at the start of the unit, we talked about an ideal gas. Every single law that we have developed so far has been for an ideal gas. But now obviously we have to talk a little bit about real gases. So when we first talked about ideal gases, I basically told you that even though some of those characteristics aren't necessarily true, most of the time they are true for real gases, which is why we could assume them to be valid. Okay, so what we find is that under standard conditions of temperature and pressure, most gases are going to behave ideally. So they're going to move in straight lines, where the hotter it is, the faster they move, the colder it is, the slower they move. They're going to collide with one another in elastic collisions, mainly because they hardly ever collide with each other. They are point masses that have no volume, because the size of the container is so much larger than the size of our atoms, so it's true. And they exert no attractive forces or repulsive forces on each other or on the container. And again, we said that was true because how often they came in contact with each other was very limited. So we find that at STP, SATP, those types of conditions, this tends to be quite true, in particular STP. Sorry, I shouldn't say SATP, but at STP this is definitely true. And that's because the gases are moving pretty fast, they're far apart, which makes their interactions and volumes pretty insignificant. But what we do find is that there are two particular sets of conditions where we find real gases do not behave ideally. They are low temperatures and high pressures. And that's because if you make it too cold, your gas is going to condense. It's going to turn into a liquid, right? It's not a gas anymore. Therefore, it's definitely not behaving like an ideal gas, okay? So low temperatures, we're going to find that real gases do not behave ideally. They're going to undergo a phase change. And high pressure is going to be the other condition, okay? So low temperatures, like I said, that one tends to be a little bit more obvious. So what happens is, as you cool the temperature, the molecules start to move a lot slower. That means it's a lot harder for them to overcome those intramolecular forces of attraction. And so we're going to find that they are going to condense, okay? That one's the easier one to understand because it's something that you actually see, right? You see gas molecules condensing. The one that can be a little trickier is high pressure, okay? And the reason why high pressure does this is if you think about a high pressure, that means we have a really, really small volume. So we've taken that container and we've shrunk it way, way, way down. And so now what we've done is we've forced all those molecules together. So we went from it being almost all empty space, not really being close together, to suddenly all these molecules are jammed tight together. There isn't a lot of space between them. They're going to be interacting a lot. There's going to be a lot of attractive forces, potentially a lot of repulsive forces. So what we're going to find is they're not going to behave ideally. You're actually generally going to find that their volumes are going to be a little bit smaller than your calculated value would give you. Okay, we're not going to ask you by how much. Literally all we're looking for you guys to recognize is that at low temperature, real gases don't behave ideally because they condense, and that high pressure is the other time that they don't behave ideally because they're going to have attractive forces, and they are going to be coming in contact with each other frequently, which was something that we said under ideal conditions. They interact so infrequently that it didn't matter. But now because they're all smashed together really tight, it is going to matter because they are going to interact with each other, okay? So one more video after this, and then you will have done all of Chem 20.